are able to have Yoshua Bengio deliver the Rockwood lecture this year. This is a tradition that goes back to the very early years of the Institute for No Computation, which was a special lecture series that was funded by the parents of a student who had graduated in computer science and had started a company, a startup company, which would, the goal was, and this is, this was actually before we were there, it was like back in 1980. So you can imagine how far ahead of the time it was, but he wanted to be able to write a program that could translate between languages. And unfortunately, he had a mountaineering accident and he was not able to see the fact that this problem now has really of language translation is completely opened up now, and it's really exciting to see how much progress has been made in the last 5 years. So one of the people who was responsible for that progress was Yoshua, and he was one of the early investigators who saw that applying deep learning techniques, machine learning techniques in general, but specifically deep learning to language problems would be an extremely important next step following the great successes with visual object recognition.
Actually, Terry, it started before. We had our first paper at NeurIPS in 2000.
Using, you're always ahead of your time, so that doesn't surprise me. But so you had the idea, but the performance wasn't quite there yet. Yeah,
that's right. We didn't have the data sets.
That's right. So it takes more than the idea and the algorithm. It also takes data and computation and actually a lot of improvements in algorithms. It was an incredibly exciting time, and it was actually during that time that Yoshua was the director for the LMB program, Learning in Machines and Brains, for the Canadian Institute for Advanced Research. He took over from Jeff Hinton, who was the pioneer for the first 10 years, I think it was, wasn't that right? Yeah. And I think we're halfway through the next 10 years. So it's been, it may be the most successful program in CFAR.
I guess in terms of impact, it's been pretty amazing.
Yeah, not just, I think, the impact has been really to change the way that a lot of people think about how we interact with computers. So, in the old days, we were basically programming solutions to problems, which means you had to be a domain expert. You have to have an expert in vision or expert in language. And that was very labor intensive, and the programs were very long and very expensive, and progress was very slow. And I think that the real shift occurred when the pioneers who won the 2000, I think it was 18, yes. What year was it, the Turing Award, Yoshua, Jeff Hinton, and Jan LeCun, which I think was long overdue, because it was already obvious that this was a real transition in computer science. And by the way, it's funny how over the years, it's what I've worked on has changed. Not the work itself, but what it's called. Back in the 80s, it was called neural networks, and then in the 2000s, it was called machine learning, and now it's called artificial intelligence. It's like, it's it's like I think it was a famous French writer, I think it was Voltaire, who said that one morning he woke up and was surprised to discover that he had been speaking prose all his life. So Yoshua has a Mila. He's director of a big institute in the University of Montreal. It's affiliated, isn't it, with the University of Montreal
And McGill.
and McGill in Montreal. And again, this is he's incredibly productive, both in terms of the students he's trained, the papers he's published, and there's only one. I mean, he's got all these great awards, but he's lacking one, which I think is way overdue. And I think that we need to make him chair of the neural information processing systems to round out his career. Somehow he skipped over that step. But in any case, no, wait a second. You have been, I think. Yes, you have.
What? I mean, I've been chairing the conference, yes.
Yes, that's right. So he has been the chair, and he is on the board of trustees of the foundation. But we need to create an award for him. A special award for
you know what, Terry? I think it's better to give awards to others. I got enough.
Well, I think that in some cases it's deserved, and I think that you are one of those who deserves it. Okay, but I've gone on too long. I have to say that he's been an incredibly good colleague and very productive in ways that have really amazed me. So Yoshua, you're going to be talking about System 2, which you'll hear about from him.
Okay, thanks, Terry. Let me share my screen. So, yeah, deep learning has been extremely successful, and it got a lot of inspiration from the brain, of course, but I think we're leaving a lot of money on the table still. And today I'm going to tell you about one direction where I think next generation of neural nets could really be qualitatively superior to what we have today. Again, through an inspiration from the brain, but a lot is from cognition, cognitive science, because I'm going to talk about high-level cognition. System 2 is really about high-level cognition. Things like agency and causality and reasoning, which obviously humans do, but we haven't yet been very successful at putting into neural nets, right? Of course, this is the kind of thing that classical AI, symbolic AI, was trying to do. But what I'm after, and a number of other people, is incorporating these abilities in neural nets in a way that's not just some artificial thing on top of neural nets. And what it can give to machine learning is something crucial, something that's currently lacking in machine learning, and that's out of distribution generalization. So what does that mean? We're used to think in machine learning about generalization as what learning theory has told us it should be, which is, you have test examples from the same distribution of the training as the training examples. It's different examples, but from the same distribution. And that's what learning theory tells us we can do. But unfortunately, in the real world and in the world of human beings and animals, the world changes. There's non-stationarities, the other agents change things around you. And so it's a different world every day. And that wreaks havoc in current systems when you deploy them. So it's a theoretical question. It's one that's inspired by how humans try to, seem to deal with this, but it's also something that's going to have practical impact if it works. So one little remark before we talk about how we could deal with out of distribution generalization is we need to change the way we even perform day-to-day experiments in machine learning to take into account that what we want to measure is how robust our systems are to changes in distribution. So instead of taking the data we're receiving and shuffling it, and then taking a random subset for training and a random subset for testing, we need to keep it as it is. And for example, train on past data and test on future data, or train on data from some settings and then test on data from other settings. That's going to allow us to see things that we don't see if we only measure generalization in the usual way, the IID way. So IID is gone. We're going to OOD. That's the thing. All right. And it's a hot topic in machine learning. Now, yeah, how is it that humans are able to do that? So I'll propose some hypotheses about that. How come that we're able to cope with new settings and much better than machines are? And this raises a number of questions, like if the distribution of the test's case is different from the training distribution, then how do we know that if any machine is or human is ever going to be able to do something meaningful? So it's got to be that we replace the IID hypothesis by something else, something maybe weaker, but still where knowledge about the past somehow remains useful. If the future has nothing to do with the past, then we're dead, right? So these are the kinds of questions that I'm going to talk about that have to do with knowledge representation and asking about how humans might do that as well. So what happens when you're faced with a new situation? For example, I've been driving most of my life in North America and driving on the right, and then I arrive in London and I rent a car and I have to drive on the left. I can't go on with my habits, right? This is, it's not going to work. It's going to be an accident. I have to think about every, decision I take with the wheel and the brake. And we can see that. We can see that the brains of human beings behave differently, and we can measure what's going on to some extent with fMRI. We see different parts of the brain being activated, and so this conscious processing seems to be crucial to deal with those changes in distribution. And so this idea that we have two modes of cognition that are somehow intertwined is something that has been a great inspiration from me. And one of the thinkers of this is Dan Kahneman. I encourage you to read his book on thinking fast and slow, precisely about these two modes. So they're called System 1 and System 2. And I have an interpretation of System 1 and System 2, which may be different from others, but here's my interpretation. System 1 deals with intuitive knowledge. It can respond quickly. What is going on there is unconscious. In other words, we can't verbalize what is going on. It happens quickly, as I said, in parallel across potentially many areas, many neurons, of course. And we don't need to think about it. I can drive and somebody talks to me. Maybe they shouldn't, but that's what happens. And that's fine. I kind of have a part of my brain that's doing the driving, and I don't need to be thinking about it. That part of my knowledge is implicit, and that's the kind of task that current deep learning is good at. All right. So now, what's System 2? The part that we're missing. So yeah, it's the thing that you do consciously, physically. The bold thing here is conscious versus unconscious. It's usually much more sequential and slow, and you can kind of apply a bit of logic there that you can explain to others. So it's connected to language. It's related to how we design recipes, algorithms, plans, how we reason, and the knowledge we manipulate to some extent. I mean, at some level is verbalizable. It's explicit. So that's what we need to integrate in current deep learning. Now, why it may help for out of distribution generalization is because what we do when we reason is we're combining pieces of knowledge that we already knew in potentially novel ways. And and that's the potentially novel ways. Like that's the kind of combinatorial advantage, which may give us a kind of flexibility to face a form of generalization that's more powerful than the regular generalization that we get with system one. All right, so that's the basis. In terms of, we just observe what humans are doing when they're doing, facing those challenges, is they attend to specific elements. They use attention. And there's been a bit of a revolution in deep learning with the introduction of attention mechanisms. In fact, Terry was talking about machine translation, and in 2014, my group, we found that if we use attention mechanism in the middle of deep learning neural nets to focus on a few words at a time when we're doing translation, we get incredibly better results. And nowadays, all the machine translation systems use these attention mechanisms. And in those days, we use attention mechanisms. We designed attention mechanisms that we call content-based soft attention. The details doesn't matter that much, but soft means we could backprop through. So we could learn through the regular mechanisms we love and being used to, how to backprop and how to attend to specific elements in the input or in the previous level of representation. So the modern incarnation of this are the transformers that have been incredibly successful, and pretty much all of the state-of-the-art in NLP is based on these things. It's also called self-attention, and it lifts neural nets from machines that can operate on sets, that can operate on vectors, to machines that can operate on sets. And that's something incredibly powerful, and almost a prerequisite for conscious processing, as I'll try to argue. Attention is also an important ingredient in something I won't spend a lot of time talking about, which is subjective experience. So there's a very interesting theory by Michael Graziano, the attention schema theory, that tries to explain subjective experience. That's the hard problem of consciousness, in terms of attention seen as an internal policy that chooses what computation to do, and that involves, as any other policy may involve, planning. And the thing that does the planning is the sort of separation between that plan and the rest of what's going on in the brain may give that impression of subjective experience. Anyway, that's a theory, of course. Attention, if we go back to sort of brain analogies, is a way to modularize computation, and in particular communication between parts of the brain. Because what attention does, as you see in the bottom right figure, is it allows to dynamically decide who talks to whom in the brain or in a neural net. So it's like we have these dynamically created architectures, essentially. So attention may also be a key for something that people have said, oh, neural nets can't do. But programming and classical AI can, which is indirection and references and basically pointers. But I think that attention gives rise to something like indirection and pointers, and the reason it does is if you have a module that is selected to send their output to another module, like we see the bold arrow in the figure. The receiver doesn't know where the message comes from. I mean, it could have received the message from any of the other guys. So what it means is that the sender needs to incorporate information about where, not just the content, like a normal, usually when we think about neural nets, we think of these numbers being sent from one neuron to another neuron, and the receiving neuron kind of knows where it comes from because it always uses the same wire. But now you're going to lose that information. And the things we're sending here are not just numbers, they're like bundles of numbers. So in that bundle of numbers, we can incorporate something like an address, like where was this coming from? Like a name, what kind of variables are we talking about? It's even better than where it came from. It's something that allows to have different modules talk to each other using the same language. And sort of this shared language between modules is also part of the theories about conscious processing, for example, that that Bars proposed, that I'm going to come back to, the global workspace theory. Yeah, so here it is. This theory has been expanded since the 90s, when Bars introduced it by lots of people, and in particular Stan Lehen, who's been continuing to expand it until very recently, and writing a lot of papers on the neural implementation of this theory. And one of the central aspects of this theory is that this communication between modules that I've been talking about is happening through a bottleneck of communication. And the bottleneck is working memory. So that's not something that the theory explains, but it just states, based on our observations and what we see from experiments with humans or animals, there seems to be this communication bottleneck with a competition between different parts of the brain that may end up with only some information coming from some of these modules being stored in working memory and somehow becoming available to everyone else as if it was broadcast to everyone. So because we have this bottleneck, we also get sequential processing, because very few pieces of information go through this bottleneck. And that means to solve a typical problem, we have to go through several steps where we focus on different pieces of information one at a time. And of course, conscious processing is, as I already said, connected to language and thoughts. And in fact, the way that we know that somebody is conscious, that sort of the base, the ground truth is a human reporting that they're conscious and reporting what they're thinking. That suggests that there is a simple relationship between your conscious thoughts, which we're going to call high-level representations, and language. So language is a kind of translation. Maybe we lose something along the way, but it's very closely related. However, it's not the whole story. Like, we all know that the pure linguistic expression of some idea is incomplete. If I say I drink water, well, what does it mean, right? I mean, how do I explain how I pick up the glass and put the water in my mouth and so on? My brain knows how to do that, but it's not something I can express verbally easily. So there's a kind of, and how do I recognize the glass of water that is in front of me? So there's like lots of things that are not being represented in that language part. So in reality, the meaning is requires both system 1 and system 2 to be involved. And that's why I'm a big believer in what's called grounded language learning, where we don't want to train our AI systems only using text, like is currently mostly what people do, but instead, just like a robot, say, or a baby, you would want to learn jointly at the level of the linguistic level, and also the low level perceptual, sensory, and motor experience. Okay. Now, what's the connection to out of distribution generalization again? And what's the connection to agency and causality and reasoning? So these are the kinds of questions I'm trying to talk about today, and hopefully I'll weave something that starts to make sense. So let's see how causality comes in this whole story. Causality is related to out-of-distribution generalization. How so? Well, if you have a causal understanding of the world, what it really means is that you can predict the effect of intervention. So an intervention is when you cause something to happen, when an agent changes something in the world, potentially changes its distribution. Thus, we are in an out-of-distribution setting, but yet you are able to make sense of the consequences. In fact, you can do even better than that. You can do counterfactual reasoning. In other words, if I tell you science fiction story, you can imagine what would be the consequences of some intervention that is impossible, like going faster than the speed of light or something. We do that all the time with science fiction. We start from a premise that's probably impossible, or at least we don't know if it is, or we can go back in history and say, what if, what if the French had won the war against the English and North America was French? So you can play those games, and you're able to do that because we have a kind of causal model in our head that allows us to unfold the cause-effect relationships, starting from any potential state, right? So that's causal understanding, and it looks like very early on, babies who don't even speak yet have a form of causal understanding and are developing their causal understanding of the world as they learn about it. So the key to the ability to generalize out of distribution is that the part of your knowledge that is transported across all these changes in distribution is your understanding of the causal mechanism. So what are the causal mechanisms? Think like the laws of physics. But that's probably not what we have in our brain. But something like that, right? Something that's stationary. In other words, whatever happens in the world, there are things that continue to be true. Those things are what allow us to generalize to new settings. The things that change are the values of variables. I decide to open the door or the window right now, and it's going to be fresher in the room. So I did an intervention. It's changing things, and it could have been different, but the kind of underlying laws of physics didn't change. So that requires a kind of world model of the effect of our actions. But that world model can't be a big black box. It has to be decomposed into the little pieces that are these stationary parts, so that I can recombine these pieces in ways that now make sense to explain a new scenario. So here's another kind of theoretical claim that in our brain we store two kinds of knowledge, basically the system 1 and the system 2. But what does that mean? There's the knowledge that is verbalizable, and there's the knowledge that is not. Right? So everything that we can explain with words, that's on one side of the equation, and everything that we can't, that's on the other side. I mean, it's not a perfectly clean separation, because eventually, if you think enough about it, you can dig a bit, but roughly, okay. And why would evolution, give us that separation? And there could be a number of reasons, but a fundamental reason from a machine learning theory point of view is that maybe there are properties of the verbalizable knowledge that apply to that kind of knowledge, but doesn't apply to the non-verbalizable knowledge. And the main property I have in mind when I'm thinking about this is the sparse dependencies assumption that I will come back to. In other words, that the causal dependencies between the variables involve very few variables at a time. And we know it's not true for low-level stuff. Like the relationship between pixels is very complicated and involves many, many things interacting together. But the relationships between the concepts that we refer to with language, they have those very special properties. So more generally, what I'm trying to say is that there may be assumptions or priors or inductive biases that are specific to system 2 knowledge. And if we can figure out, or at least come up with hypotheses first about what these inductive biases may be, then it's going to be much easier and rational, sort of scientific, to test those things by putting them into machine learning models and see if we can do those things that humans are good at using system 2. All right, so now I'm going to go through a few of these inductive biases, kind of assumptions about the nature of system 2 knowledge and the variables and mechanisms that are being manipulated at that level. So the main one is the one that I just described, that the dependencies are sparse. To illustrate this, consider any like one sentence, reasonably short sentence description of something, like if I drop the ball, it will fall on the ground. You notice here that this is making a prediction about the position of a variable, the position of the ball. Sorry, it's making a prediction about the value of a variable, which is the position of the ball. And I'm able to make that prediction using 2 or 3 other things, like where was the ball before, if I was holding it, and then did I drop it, or something like this. 3 things. So predict one thing out of 3 things. And the prediction is pretty good. Like, yeah, it will fall on the ground. It's 99.9% sure. Now, this is an amazing property. You don't get that with pixels. Try to predict 1 pixel given 3 other pixels. It doesn't work. So it's like if we have in our head these abstract concepts that have a special property that you don't have at the low level, and having those special properties could really allow us to do things easily that are not so easy with the low-level representations. Okay, so that's kind of the central hypothesis, and it's consistent with the global workspace theory. How is it consistent with that? So the global workspace theory is sort of descriptive. It's saying, well, we have this bottleneck where very few variables at a time come in and are being broadcast to everyone. I mean, everyone in the brain, every expert in the brain. So that's kind of a description, but why would that be useful? Well, it would be a way to enforce that sparsity, because if at the system 2 level, you're only able to jointly see very few things at a time, things that you have in your mind at this moment, then you can only represent these very sparse dependencies. That's kind of a constraint. It's a hard constraint. So the architecture constraint is forcing that inductive bias. So that would be an explanation why we would have this bottleneck, because otherwise, like, why would we have this crazy bottleneck? I mean, the brain is huge. It seems strange that we have such a small working memory, and why not connect things in a much more, well, you can't have n-squared connections, but you could have something that doesn't have such big of a bottleneck, right? So, so that's the main assumption. But then tell about some related things. So the connection to causality, like these high-level concepts, we reason causally with them. So if you think about the words in a sentence, they often are connected to causal relationships. You talk about entities that can be cause, effect, agent, action. You can describe the action, the mode of the action, when it is, where it is, and so on. And you can use language to do the powerful, causal things, counterfactuals, things that don't even happen in the world, but you can just imagine, like science fiction. And that's useful. It's useful for credit assignment, for example. If I had acted in this way, I would have succeeded in my project. So that's extremely useful. And another property of these high-level variables is that they're related through these mechanisms. I keep talking about these causal mechanisms. And these mechanisms are reusable. So for example, the dropping mechanisms or the inertial mechanism of things moving in space or whatever, they apply to my phone if I drop it, but they could apply to any other object. In fact, I think I had a ball previously. Oh, sorry, I had a ball and now it's a phone, right? So, and here's like another thing, some object that I didn't know about, a Zog. So that reusability is very powerful, and I'll come back to that. But it also allows us to generalize. For example, if I say, if I had dropped the Zog, it would have fallen on the ground. I can guess a lot about what the Zog is. It's some object, and it's one that I can hold in my hands, and so on. And then these reusable mechanisms, they're more than reusable. Okay, that's a strong hypothesis now that I'm making that comes from not cognitive science, although there is some relationship, but from research on causality. These mechanisms are algorithmically independent. So this is a hypothesis that I've learned from a 2012 paper by Bernard Shopkoff, and Bernard is, I would say, one of the leaders of the causal research in machine learning. And he and his collaborators have an amazingly good book if you're interested in the last few years on causality. But anyway, so this hypothesis is that the mechanisms are independent in a way that's different from statistical independence because they are not random variables. What does it mean to talk about independence? So algorithmic independence, you have to understand, is there's no information about one mechanism that you can get from another one, except for the API, like the constraint on the arguments that they send and receive to each other. The mechanisms are independent of each other. It's like, think about pieces of code. So you'd like to design your your code, break it into modules such that if one of the modules were to change in the future because I had it wrong or whatever, I don't need to change the rest of the code. So that's algorithmic independence. Formally, what it means is I can't compress the two pieces of code better by looking at them together than compressing them separately and adding up the lengths. Okay, so that's an interesting property, and there's actually a recent ICML paper this year that studies how learning algorithm should be designed in principle to achieve that property. So modular learning algorithms, where the system is composed of modules and the modules are learning, but they can communicate with each other or compete with each other or whatever. But you want them to have this algorithmic independence property. What are the kind of conditions that are necessary for this? Another very obvious property of the high-level variables that we manipulate with language and we manipulate in our thoughts is that, to some extent, and maybe a large extent, many of these entities that we're manipulating are discrete. In deep learning, we manipulate all these real value things. Maybe they're corresponding to firing frequencies or whatever. But there's a graded notion there in all these computations that seem to work so well for vision and speech and so on. But when it comes to the kinds of things we communicate with language, it seems that there's somewhere in that process a propensity to discretize. And why would that be a good thing? It's like another bottleneck. So I've talked about the bottleneck, we throw away information, right? Why would it be good to throw away information? Well, it's because it helps us to generalize to the things that we are throwing away. If different brain modules communicate with each other through discrete messages like categories, then I could have another module that learns the same language of communication and can use the same tokens. And so the modules can be hot swappable for one another. So you get this ease of recombining different modules that is harder if they communicate with continuous values, because it's going to be hard to get exactly compatible continuous codes. So that may be, at least that's a hypothesis. And there seems to be evidence that we see this kind of discretization going on in the brain, in particular in the hippocampus, and in decision-making. We see that discreteness emerging as a result of converging to fixed points. So there's a dynamical system effect here that yields the discreteness. It's everything is continuous, but when you have a fixed point, you end up with discrete things. All right. Another really important property that has to do with actions is that the interventions, that they're like high-level abstract actions, and they refer to a single object. They're interventions that modify a single object. I mean, we can be messy and aim for a single thing, and then we miss and we touch a bunch of other things. But our intention is typically to only touch one thing. And that thing itself, you can have effects. That change can have effects downstream on a lot of other things. But the causal chain starts with an agent controlling a single object. I mean, you can have a sequence of actions and so on, but they're the atomic elements of these intentions and interventions seem to be very sparse, that you focus on one thing that the action aims at. That means that means that's related to the notion of affordance, right? In psychology, and I'm going to come back to that actually maybe right here. So when we're thinking in deep learning about representation learning, typically we think about representing objects, entities in the world. And that's good. But we have the other guys doing reinforcement learning who are thinking about abstract actions, options, temporally extended abstract actions. And these two worlds need to talk to each other, because these abstract actions, as I said, they will target one object at a time. And the objects will have affordances which correspond to which abstract action can be done on them. So you don't want to learn these two spaces, the space of abstract objects and the space of abstract actions, separately. They need to be defined in terms of each other. So that's another inductive bias, which we started thinking about a few years ago, but I think there's a lot of potential for more words and more work in that direction. Okay, so I'm done with the inductive biases. I'm going to now, like, in the next 15 minutes, tell you quickly about specific papers in the last few years. I'm going to go very quickly on each of them. Just what was the main thing we studied, and I'm happy to share my slides, and if people are interested to follow up on these things. One of the early papers on this is something we put on archive in 2019, Well, actually, the first paper that I did on this theme is a 2017 paper called the Consciousness Fire. But there was no experiment there. It was just all my kind of being excited about conscious processing is something we need to put in deep learning, and making the connection to the global workspace theory, and talking about the sparsity assumption. That's the one I mentioned earlier. In 2019, we had a first paper which ended up being published in 2020, last year at ICLR, showing how you could discover both representations and the causal structure, at least in this paper, only like very simple scenarios with two variables, and then later papers by Kay and by Brouillard, larger graphs with more variables. And I hear that now there are people applying these techniques to graphs with thousands of variables. So we started small, but we showed that if you take advantage of the inductive bias that the change due to an intervention is localized, you can actually discover whether A is a cause of B or B is a cause of A through the observation of changes in distribution. You don't need to know what the change was. You don't need to know what the intervention was, but just the fact that there was a change. And now there are people working on how you detect that there are changes. Is actually a very strong signal to discover the causal structure as well as the causal variables. In other words, map the low-level data to the right space. So this is what this figure is supposed to illustrate, which is in the paper, I think. Let's say the data was generated by two variables, A and B, that are like the ground truth, cause and effect. A is the cause, B is the effect. But what we observe in the real world is a transformation of this. Like it's been, their joint distribution has been rotated. So the learner sees these pairs of points that have that joint distribution. And in the XY space of observed things, it's not obvious that there's even a notion of causality. But if the learner can discover a transformation into a new space UV, that somehow up to permutations and scaling is analog to the AB space, and it can discover a causal relationship. Let's say U causes V or V causes U. And the kind of objectives that we started studying seem empirically to allow to discover these things. And then the Brouillard paper shows some theorems, but I think there's still a long way to go in terms of theory there. So these are the papers that generalize this on larger graphs, K and then Brouillard, the last NeurIPS. And there are lots of interesting details here, like how do you deal with graphs that have, the number of graphs with a certain number of nodes is exponential. So how do you even like learn the graph? And now, I'm thinking of new ways to do that are more neural. But in those days, we just tried to figure out for each potential edge, what's the probability that it's there, and if it's there, should it be one way or or the other way? Which one is cause, which one is effect? And so we would learn these coefficients, these probabilities for each edge, and then the mechanisms that relate the variables. Once you have a graph, you can say, well, A depends on B and C, so there's a little neural net, which is this little causal module that relates A, B, and C together, and we train these neural nets. In this case, is one per variable, and nowadays we're thinking differently, but this was really early days. That predicts one thing given some subset of the other things, and which subset depends on the graph structure, which is also what you're learning at the same time. Another thread, quite a few papers came out of my group on modularization and attention. So I've talked about attention already before, and I mentioned how we could use it to control the communication between different modules. So the first paper on this we put out in 2019, and we call it Recurrent Independent Mechanism. That was finally published this year at ICLR. And what it is just you have a recurrent net, but instead of having fully connected recurrent net, we're going to divide it into modules. It's going to be fully connected inside each module, but then between modules, we're going to have this attention mechanism that controls who can talk to whom, and it's going to be sparse. So each module is going to compete with the others to win the right to be listened by others. So that's the basic architecture of the RIMs, and that worked nicely in a number of problems. And then we extended it to make the communication actually have a bottleneck, like in the global workspace theory. In other words, there's a specific pattern of constraint, which is few modules are winning the competition to write in the workspace. The workspace is now seen as a set of entities. So by the way, remember that now we have these attention-based architectures in deep learning, and that means we can design architectures that work on sets. So working memory can be seen as a set. Think of a set of slots. So there's no ordering here. It doesn't really matter. And so the modules which win can write in those slots, and then the content of those slots become available for everyone else. And that's one step of computation. You can repeat that many times. It's recurrent, and that's it. So it's just a variation on the RIM, on the recurrent independent modules mechanisms. And it gives better out of distribution generalization. So this constraint on the architecture seems to work. So it seems to validate the not just with the linguistic analogy that I used earlier, but through machine learning experiments, this bottleneck hypothesis of the global workspace theory. Concretely, for example, let's look at the column B here. For people who know about transformers, which is the modern incarnation of attention-based neural nets, instead of having each layer that has a bunch of elements and vectors being available for the next layer, these elements are going to compete with each other, and only a few are going to be going to the shared workspace. So we introduced this bottleneck, and just a few guys win, and then everyone else at the next level can read from there, and then we do that over and over again. So that's how that architecture works. And you can apply it to different kinds of architectures, but it's this bottleneck idea. A related paper that's been also presented at the last ICLR is sort of strongly inspired by cognitive science with Mike Moser, and it's called Object Files and Schemata, Factorizing Declarative and Procedural Knowledge in Dynamical Systems. And what it does compared to the sort of modular architecture I already talked about is it thinks of the attention mechanism not just as selecting one content, like what goes into working memory, but also selecting one mechanism. So here in that paper, the mechanisms are called schema. Think of them like rules, and the contents they're called object files. And so we have a double attention mechanism, which we have this joint competition. Every object file, every entity in the working memory is competing with the others, and every possible rule, which we have a large pool of, presumably, every possible mechanism is competing with each other, and there's this joint competition to decide which rule is going to be applied to which object. And then more recently, this is a submitted paper. We have a thing called neural production systems, where we extend this idea where instead of just picking one object and one rule, we can pick multiple objects and one rule. So it's a many-way competition. And also another difference is, unlike in the previous paper where you could have multiple rules being applied in parallel, this is sequential. So you only pick one rule, and a set of arguments that it applies to. And then that changes the workspace. And then again, there's competition and another rule and its arguments get selected. And from a brain perspective, the arguments could come from working memory, but they could also come from longer term memory. And they could be selected from perception. There's something out there that attracts your attention. So and that is a pretty cool paper where we show that we can change the focus of attention of people working on disentangling. I introduced that term to talk about disentangling factors of variation, like the high-level entities, the concepts, the causes and effects, to disentangling the mechanisms, disentangling those rules. What are the rules? And how do we decompose knowledge into those pieces? That's what really gives us an advantage in terms of out-of-distribution generalization. So in the neural production systems paper, we show toy problems where the learner discovers the right separation of knowledge into pieces, like it operates on numbers and it discovers that addition, multiplication, and subtraction are the right concepts that it needs, or in the case of images, like these endless images that are undergoing transformation, discovers that there's I guess for different types of operations that explain everything really, and you need to separate them. And then last paper I think I want to mention is this one called Discrete Valued Neural Communication. And it's about this discreteness inductive bias that I mentioned for the communication bottleneck. So imagine you have communication between t and t+1, and it's going to go through a bottleneck. In addition to that bottleneck, we're going to have a discretization bottleneck. So the way we implemented this and still allow backprop to proceed, because when you discretize, gradient is 0, is using what's called a straight-through estimator. So the idea of straight-through estimator actually comes from Jeff Hinton, and then I kind of worked on this and wrote a paper in 2013, I think, in the context of neural nets with discrete outputs for each unit, and you'd like to backprop through these things. So here, in the last few years, there's been a lot of approaches to do different variants of straight-through discretization, and we used a particular one that's been popularized in a paper called VQ-VAE, vector quantization variational autoencoder, and that works really well here. So what we do is, let's say that we want to communicate 3 vectors, and we're going to discretize them. We're not going to discretize them to a single symbol like they do in the VQ-VAE, but we're going to have 3 symbols, because that gives us a combinatorial advantage in terms of expressive power. But they're going to share the same codebook. It's like this is the same language. So that codebook maps a vector to an integer, and back, an integer to the prototype vector corresponding to that code. So the encoder is going to transform its real valued vectors into a list of symbols, and then the receiving module converts back those symbols into vectors. And then there is a formula to approximate the gradient through that whole channel that works pretty well. It's a heuristic, and it approximates the gradient, obviously, but it does a good job. All right, so now to approach the conclusion of my talk, let me say a few words about what we're doing now that's not in any paper yet. We're thinking about generative models that can be used to reason, to propose partial graphs of explanation. So what I mean by an explanatory graph is something where the nodes correspond to events that happen, or these entities, variables, and so on that we talk about with language. And then those nodes are connected to each other through these mechanisms. So we have a pool of rules or mechanisms, and the generator decides on the fly which variables, which entities, which events to pay attention to put in the graph, and which mechanisms are relevant, and how to connect all these guys together to form a graph. And that graph you can think of as a story. Like, I see a video and I say, the black cat is running after the squirrel, and the squirrel climbs the tree. So this is something I could represent as a graph that involves all of the events, actors, and mechanisms, actions that are involved. So how do we learn to generate such explanations in an unsupervised way? I mean, I'm not saying, have humans provide language that explains the video. That's been done and doesn't work. But how do we represent knowledge about the world and discover knowledge about the world by both learning those mechanisms, like the causal relationships that can exist, like verbs, if you want, and the types of variables, and how these mechanisms can or not be applied to different types of variables, and how to take raw data and map it to these kinds of explanations. That's the inference part. Yeah. So now we're back to generative models that I won't have a lot of time to talk about, but there's a lot of exciting things going on now in my group around this. Let me finish by making a little bit of a contrast between the research program I'm highlighting and the symbolic AI research program. So in a way, we're trying to get the best of both worlds. All the things that have worked really well for us with deep learning that you lose with the classical rule-based AI symbol manipulation. So we want to keep efficient large-scale learning. We want to keep grounding the high-level concepts into system one knowledge, implicit knowledge. We want to keep distributed representation so we can take advantage of the generalization power that comes from that. We want to use system one to be able to search in the high-level space. This is something I didn't really have time to talk about, but think about what is going on in AlphaGo. In AlphaGo, you learn a value function. That's a system one thing. It's hard to decompose how, it's what's going on inside the value function network. But that value function allows you to prune the search tree. In fact, you can even just do one step look ahead, and it's already very powerful. So that's a system one ability that is important for system two tasks, where you potentially need to search through all these explanations, all these graphs, all these plans. There's an exponential number of them. So we need these search mechanisms, and I'm betting on kind of generative search mechanisms to do that. Also, modern deep learning can handle uncertainty in many ways, and this was a little bit more difficult with classical AI. But we want to incorporate things that come directly from classical AI, like systematic generalization. You can apply the rules to new things, and you can combine rules and still make sense, hopefully. Well, in classical AI, it didn't, because they designed the rules by hand, and then it didn't always make sense. But if we learn, we can make sure that this is going to work. And yeah, and then of course, these rules, they're like pieces of knowledge, and they don't have to be symbolic rules. Okay, I've used the word rule, but really I mean like little parts of your brain, little MLPs. The important part is the modularization. So we are factorizing knowledge into small exchangeable pieces. That's the thing that is present in classical AI, is not present in the standard kind of neural net architectures, but we need to have that to get the out of decision generalization power that I've been talking about. And then of course, another property of the symbolic AI program is that comes with the exchangeability, right? It's the indirection aspects. It's that you're being able to manipulate references and making a distinction between variables and instances and things like that, which is again not so natural with standard classical MLPs. And yeah, so I've talked about many things, that are interestingly connected to each other. Hopefully, there is some sense in what I'm saying, and hopefully it makes, there's something you can take out of it. And thank you very much.
Thank you. So we have time for perhaps a few questions.
I wanted to just before we have questions is to point out that this really takes us back to the very beginning of the Institute for Neural Computation, because we inherited the license, the ORU license, from the Institute for Cognitive Science, and this is really coming back to that. It was this is what was interesting was that we were able to transfer license because we convinced the University of California that's really the same thing.
That was a trick.
Well, it was a language thing. We're just going to change a few words, and basically we have the same goals, and we're going to try to make progress. But and let me also add that some of these themes that you've heard today about causality and dependencies and so forth are going to be covered in a workshop at the Neural Information Processing Systems Conference coming up in December. Yoshua and I and Judea Pearl are organized, and several others are organized, have been given a slot for one of the workshops, and it's causality. Why now? And if you, each one of us has one of those words. Of course, Judea has a book called Why, so that makes a lot of sense. Which word do you want, Yoshua? If you don't want it, I'll take now. You can have causality.
Yeah, I don't think I want to own one of these things. It's for everyone to grab.
Well, it's modular. That's the way we're thinking. Right. Okay, so time for questions, and I guess we have. I'm going to go to chat and to see if there's any here. Does anybody?
I see a bunch. Somebody needs to triage.
Yeah. Okay. So I'm going to start out. Let's see. Yeah, I'll do the triage. Okay, Pat Churchill, and to everybody. Yoshua seems to suggest that only humans have system 2, only verbal humans. This is problematic.
I didn't say that. I said that it's an easy way to make the distinction. I don't know what's going on with other animals, and in fact, the whole study of conscious processing in other animals is hard because we can't interrogate them. But my suspicion is that it's not a black and white thing. Remember, I already told you a bunch of inductive biases, and I suspect that we share a lot of that with other animals. Now, the fact that they don't verbalize in a strict sense is a different story.
Okay, Pat, do you want to add to that since it was your question? You have to unmute.
Yeah, I think it's kind of good to make that clear because in your talk, there really is a very strong emphasis on the idea of verbalizability and about language being the thing that draws certain kinds of boundaries for us. But there are quite nice data, especially actually from dogs, showing that they have really very sophisticated capacities for doing what you might call counterfactual reasoning. The other thing, though, that kind of troubles me a little bit about your really very warm embrace of System 1 and System 2 is that Danny Kahneman himself said, there really are not two systems. And these are really kind of fictitious characters that we put into place in order to kind of dramatize a point. And, many of the conversations I have with Terry are all about how modularity, from the perspective of neuroscience is getting really, really problematic. The boundaries are fuzzy. We see motor signals in visual cortex and so on and so forth. And so I think, it occurred to me anyway that your strategy may be really powerful in the context of neural nets and AI, but it may not actually fold over quite so gracefully onto the neuroscience and the psychology itself. But thank you for a wonderful talk.
My pleasure.
So there is a mapping. I mean, this is very crude. As you point out, Yoshua, the system one is really the automatic system that we know is part of the basal ganglia that has a loop between the cortex. Cortex projects to it very rich representation, and then it has to make a sequential decision of what to do next, right? And then that comes back, and that's found in all species. Basal ganglia goes back to early vertebrates, right? And there's an equivalent to that. So that part that's good. Okay, that's the foundational stuff. That's good. And learning through dopamine, that's a fantastic advance that's occurred in neuroscience. The reward prediction error that now is used in reinforcement learning in AI. But I think that your idea that there's a bottleneck is certainly true. In terms of the intuitively, we have this feeling, and the psychologists talk about the number 7 plus or minus 2, but it turns out to be more like 3 or 4. Off by a factor of 2 or something. But that I would very much mistrust anything that's intuitive. In other words, I think that's what really misled the founding fathers of AI into thinking that, oh, it's really clear, what I'm thinking, and I can just automate that. And I think that it hides a lot of the complexity of what the real problem is.
Sure. Let me respond to Patricia a little bit. So I'm trying to understand things at a very high altitude here, and I'm not a neuroscientist or a cognitive neuroscientist, but I do talk to these people, it's the fact that we may have this modularity doesn't mean that the modules don't talk to each other in other ways than through the bottleneck. So, for example, in things that we're working on right now, you can have local connections, for example, or you could have connections to the motor system, as you said. In fact, you may want to have those things. So the bottleneck isn't the whole story about what is going on in the brain. It's something that imposes a constraint on some of the knowledge that is represented that would provide this ability to generalize in this powerful dynamic way that we seem to enjoy when we're facing new situations.
But don't you think that the bottleneck is probably very ancient, and it comes about as a result of the fact that there's only a limited amount that any organism can do at one time? I mean, there's only a certain amount of motor operations that I can do at a given time. I mean, yeah, my heart goes on by itself, but in the domain,
but you're doing a lot more. You're doing a lot more in parallel.
In the domain of voluntary motion, there's a limited amount that I can do at a given time.
One word at a time.
And that's at the level of your intention, but actually you can have hundreds of muscles that are being involved in one, to one reaching movement or one.
Well, of course, of course.
So, that's what I mean. Like that, it's the bottleneck is happening at an abstract level.
Not so sure.
So look, you can only say one word at a time, right? Now you may be thinking a dozen things, and maybe and it's all somehow getting set. Where is that decision being made? And we're pretty clear now that it's in the basal ganglion, right? This automatic system is actually making the decision of what movement to make, what word to say, and that goes sequentially. And that's what I think what Pat is getting at. And you somehow you have to be able to make a decision. Right? You can't do three things at the same time, although some people try to do that. Doesn't always work well.
Yeah, I just mean, I think that the bottleneck, I love this story of the bottleneck, and I think in the context of your project, it's very workable. But I think in the context of the evolution of nervous systems, the bottleneck may have its source in motor control. That's all.
Okay, yeah, that would make a lot of sense.
It would.
Okay, good. Well, we've solved that problem. Okay. So here's another question from Chris Emazu. What impact or insight from GraphML can be applied to causal reasoning? For example, in your research with factor graphs, you said graphs were able to effectively represent situations like the cat chasing the squirrel and the squirrel climbs the tree. My question is, how useful do you think GraphML and knowledge graph representations will be in System 2?
Yeah, so I think they're interesting tools, but the kinds of graphs that I'm talking about are slightly different. I think the nice thing is we've made a lot of progress in deep learning with handling graphs. The kinds of graphs, like the dynamic causal graphs that I'm thinking about, they're different because it's not being designed by a human. So current graph neural nets, the graph structure is human provided. In knowledge graphs, it's even worse. It's the structure and the semantics of the nodes is provided. And here I'm thinking about systems that make up the graph themselves, as well as the semantics of the nodes. And you can think of them as just the top hidden layer of a neural net, except that instead of being a vector, it's now a structured thing that implicitly represents a graph, like the story about that video.
Good. Okay. So yeah, there's graphs are in the air. I think that the question is,
yeah, for sure.
Yeah. Let's see. Okay. So here's a question from an engineer. In fact, he puts a star by that. He says, we augment what we understand with computation and calculations. And your analogy of the system 1 and 2 system 2 thinking, I'm wondering how you see traditional computational sciences that can be used, that we already are using in engineering and sciences. How is what you're doing going to be
computational sciences?
Traditional computer science, I guess.
Yeah, I mean, machine learning is machine learning. I mean, in the same sense that machine learning is part of computer science, but it's very different. Yeah, I'm not sure I understand the question. Yeah, go ahead.
Yeah, so I'm talking about like traditional mechanics calculations, P.D. based physics. So there's a lot of stuff, obviously, with the physics informed, physics guided machine learning and things. But obviously, machine learning is that we're ever going to use. We're also going to be using all these other stuff that we have been using. So I'm just wondering how that augments your system 1, system 2. Is that an augmentation of system 2, or do you see that as a system 3 that needs to be augmented into the future?
Okay, so first of all, I'm interested in like what's going on in I mean, the kind of capabilities that a child has. So they don't do PDEs, at least explicitly, right?
No.
You're talking about an application and maybe in the real world where we want to incorporate physical knowledge into machine learning. Mm-hmm. I'm trying to do AI in the sense of reproducing the abilities of humans. Now, that being said, I think there are connections. So one of the exciting areas at the intersection of physics and machine learning, is discovering new simplified laws of physics that allow to make simulations much faster, but maybe satisfy some of the principles we know from physics. And people are trying to use neural nets right now to accelerate physical simulators that are way too expensive, for example, for climate or molecules. And it works really well. Like they can go like 1000x faster, but they're not interpretable. You get these black boxes that are fast, but we don't make sense of what's going on. If instead of these black boxes, we had these kinds of system 2 architectures, maybe it would become much. Basically, the constraint would be it's looking for explanations that are verbalizable. I mean, that can be described through the same kind of language as we use natural language for. So that would increase the chances that humans could understand what the machine has learned.
It maybe even talk to the machine.
And maybe even talk to the machine, right? So if one of the promises of doing the system 2 stuff is, from an AI perspective, is it will make it easier for humans to like just add a new rule, right? Like if I tell you, let's play this game, and I give you the new rules, right? You can do it right away, and it's not so easy to do that with current machine learning. But if you have a representation of the kind I'm talking about, then it's much easier for humans to interact at that level and provide knowledge at that level.
Sure, and I guess what I'm sort of curious about in the long-term future, that we, as human and machine interact, I'm just looking at it from engineering perspective, that we do these things. That one of the main things that we have a lot of difficulties with, and I think perhaps in the future, this sort of what you're sort of doing might be able to help us, is actually interdisciplinary communication. So if I'm talking to a physicist versus a chemist, or aerodynamicists versus mechanicians, or people like that, and then same words, if you're talking about discretization and different words, and same words meaning different things, or maybe the overlap, there's an overlap and the subset of the meaning, but there was a sort of meaning that are slightly different. There's a lot of these complications that actually has real consequences in the final design that we have, that these sort of things get confused. And I think that's where a lot of the complexities actually arise, in unintended consequences of complex systems, at least in the mechanical engineering and aerospace type of engineering system. So I'd be very curious to sort of see how some of the things that you're talking about could potentially be applied to communications between different disciplines.
Okay, well, I think we've had a wonderful presentation, very, very provocative and also illuminating. And I just want to, the Zoom meetings kind of end very flat because you can't applause, but I will. Okay.
Thank you.
So we're going to take a 5-minute break. Is that right?
Yep.
And who's going to introduce someone should introduce the next session that we're going to have. Who's organizing it? It's going to be on ethics, right? Gert, are you the organizer?
No, this is we have Gary Cottrell and we have Pat Thursland. We have a great team there.
I think
Okay.
Roger should introduce it.
Okay, well, it doesn't look like it's very well organized, but it looks like we have a great group. So come back in 5 minutes and we will have a discussion on neuro and AI ethics. Same place, same time.